Hello, statisticians. Mr. Youngsaver here from Skew the Script. Today we're going to look at equality of opportunity for low-income students in American schools through the use of least squared regression line modeling. Let's skew it. Today's lessons cover the least squared regression line. This is Unit 3, Lesson 2 in our sequence. Our main focus area today is talking about, for low-income students, often school is seen as an equalizer of opportunity in the United States, a place where opportunities can arise for people who come from lower income backgrounds. At the same time, being from a lower income background often brings challenges with it in going to school and being successful in school. So the main central question I want to ask is, do schools in America effectively equalize opportunity for low income students? And the angle we're going to take specifically today is, will raising attendance also raise scores for low-income students? And I'll explain why we're going to take that angle exactly. We're going into the guided notes now. If you'd like to follow along, please go to the website URL here to find the handout. And we're going to start today with the least squared regression line. Nationally in the United States, we know that there is an income achievement gap. Specifically, we've seen in standardized test scores that lower income students tend to perform worse than their higher income peers. And many people have thought about, why is this happening? Have thought about, what can we do to change it? At the same time, we've also noticed that there's an income attendance gap. Specifically, lower income students go to school less often than their higher income peers. There are forces at work that keep lower income students away from school compared to their higher income peers. So people wonder, is this a true correlation? Is there a correlation here that maybe we can provide a solution for? And there have been many articles, many research studies, and many school districts have made policies around this. For example, some studies claim that we can reduce the achievement gap or even close the achievement gap by specifically focusing on attendance. So that model of thinking goes like this. If people experience poverty, their attendance tends to be lower at school, and because they're missing school, they get lower test scores. If we change their attendance to have a higher attendance, then being in school more, their scores will increase. So that's the central question we're going to ask. Will raising attendance also raise test scores? And many districts have tried this, and we have some interesting results that we can look through the data here. We're going to use linear regression, and specifically, I've got some data that's a random sample from some students at a Texas school. We have the percent attendance, the percent of school days that they attended, and their Algebra 1 score. These are 9th grade students taking Algebra 1. This is the state standardized test at the end of the year they take. This is their raw score, the number of questions they got right out of the total. In this case, the explanatory variable is the attendance, which is explaining the response, how well they did on this test. So the X variable is attendance, the Y variable is test scores. If we graph these points in a scatter plot, we can describe this distribution. It looks positive with no outliers and linear and strong. So the superintendent of the school district might ask, if a student meets our minimum attendance goal for every student, which is say 87%, what would their predicted score be based on this distribution? So we can fit a model to it, and we notice, yes, it's positive. As percent of school days attended goes up, so do test scores. So we can use this model to make predictions. But first I want to ask, how do we find this model? What's the exact way that we find the best linear model to fit to this data, the least squared regression line? So here's some more simple data, just 5 data points. And there's a couple of models we could fit to this. It looks positive, a little bit weak. We could do model A or model B. Model A, model B. It's not clear to me which is better, A, B again. Well, let's think about, with these two models, again, the same data set, but now displayed here with the 2 different models, how can we determine which model would be the better one? Let's look at what's called the residuals. We're going to talk about residuals in depth in a later lesson, but for now, residuals are the distance in the response variable, or the Y variable, between each data point and its predicted value in our linear regression. So it's basically the Y distance between the point and the line. Here's one data point, 7, 5. And in model A, the predicted value at an X value of 7 is a Y value of 3. For model B, the predicted Y value at an X value of 7 is 4. So we can see that the residual is going to be lower for model B than for model A. The way we calculate the residual specifically is we take the observed y value, the actual data y value, minus the predicted y value, the y value on our linear model. So let's do that for each of these. 5 minus 3, take the actual observed y value minus the predicted one, is 2. 5 minus 4 is 1. So as we said, the residual was smaller for model B for that point. But then for another data point, we see an opposite trend. For this data point, which had a value of x 9 and a y value of 3, in model A, our predicted y value was 4. Whereas in model B, our predicted y value was much higher at 7. So the residual has a higher magnitude now in model B. In this case, we have a negative number because we overpredicted the data point. We take the data point minus the prediction, we get -1 for model A, we get -4 for model B. So the first thought we have is, let's make a line of best fit that minimizes the sum of these residuals. The best line we could do is one that you take the sum of all those errors in our model, and the one that is the minimum sum, that's the best fit. So let's take 3 data points that are actually already in a line, and we fit the line to them. The residuals are 0, 0, 0. There's no distance between the predicted y value in the line and the actual y value in the data point. So this is a great fit. Awesome. But what if we make this? Obviously, this is not a good model for this data. The residuals are balanced here. There's a +2 residual for when we underpredicted and a -2 residual for when we overpredicted. So we sum those residuals, we actually get 0 again because the positive and negative cancels out. Is this a good fit? Obviously, it's not. So we need to come up with a better definition because the sum of residuals were the same here, yet one model is clearly better than the other. What if instead we take those residuals and we square them? We take the +2 and the -2, we square them. So we get essentially the square area in that residual. -2 times -2 is +4, +2 times +2 is also +4. When we square, the negatives go away because we're multiplying. So now when we take the square residuals from both of these models and we add them together, obviously the model that was a better fit, 0 times 0 is still 0, and the sum of the residuals is still 0, whereas the residual square sum for the worst model is now 8. So now we see, okay, the model on the bottom is better. So that's how we define the least square regression line. It's a linear model that minimizes the sum of the residuals squared, or the square residuals. This is also called the line of best fit. So that's how we find the least square regression line. We take the residuals, we square them, and then we find the version of the line that minimizes those square areas, essentially. We're going to have calculator steps to this. You're not expected to do it by hand in a later lesson. So let's talk about different aspects of that line that we're making, the slope and the y-intercept. So this is every mathematician's favorite one-liner, y equals mx plus b. You know it very well from Algebra 1. And let's talk about the different components of this. Y equals mx plus b. What's the slope? M, or 2. And the slope, what does it mean? Well, it means that when you go over 1 on the x-axis, so you go up 1 on the x-axis, we raise up 2 on the y-axis. So it's the rate of change for y given a 1 unit increase in x. Now, the y-intercept here is 1. And what does that mean? Well, when the line crosses the y-axis, it does so at a y value of 1. When x is 0, in other words, so at the y-axis the x value is 0, our y value is 1. We have a very similar equation in statistics. The linear regression line is very similar to the linear equation line from Algebra 1, except the order is a little bit different. Now, some textbooks will do this a little bit differently. I'm going to go with this version that corresponds to a lot of the multiple regressions we see later in statistics. But the important point is that the variable next to the x in our model, which is b, the variable next to the x, the coefficient of x, is the slope. It's the one that kind of modifies x. It's the rate of change for y given x. So that's the slope. And then the coefficient that is a constant that doesn't have an x next to it is the y-intercept. In the linear equation, it's b. In our stats equation, it's going to be called a. So this is the correspondence there. And then one other note to difference, in a linear equation in Algebra 1, we have a y value. In a linear equation in statistics, we have a predicted y value because we know there's variation, and this is going to be our prediction of the y value, knowing that the actual y value of a real data point might be a little bit different given the random variation in a situation. So here's our linear regression equation, and when we calculate the regression equation here, which we can do with a calculator, again, that's going to be a later lesson, we get the following. Our y-intercept is -7.69, and our rate of change, our slope, is 0.57. When we write out this linear regression equation, this is really important, you need to always make sure to label your variables. Y hat is the predicted test score. In this case, X was the predicted, not the predicted, the percent attendance. X we know, and so for a given attendance, we're predicting the student's test score. So let's interpret that slope value. The slope value was 0.57, the one next to the X. That means, just like for linear regression, for a linear equation, for every 1 unit increase in X, our Y variable is going to increase by a value of 0.57. So for every 1 unit increase in the explanatory variable, our model predicts an average increase of our slope value of 0.57 in the response. The way we do that is here. If the slope value is negative, it would be a decrease. So for every 1 percentage point increase in percent attendance in our explanatory variable, our model predicts an average increase of about 0.5669, which was 0.57 points in a student's test score. That's the interpretation of the slope here. For the y-intercept here is negative 7.69. So that means at an X value of 0, our Y value is going to be negative 7.69. So when the explanatory variable, attendance, is 0 units, so when attendance is 0%, our model predicts the student's test score, they would get negative 7.689 questions right. Obviously, that doesn't mean anything. In this case, the y-intercept is not meaningful. Since anyone with 0% attendance doesn't really go to the school. They've never been to the school, they'd probably be withdrawn from the school. There's no student who is 0% attending the school and also taking this test. Anyone who doesn't come to school is not also be taking the test. So this is a meaningless y-intercept value. That's why it's a negative, and it doesn't make sense also to have a negative test score. So sometimes the y-intercept won't be meaningful if the X value, which in this case is 0% attendance, is also not meaningful. So that's something to keep an eye on when you're interpreting your y-intercept. Now let's make some predictions using this least square regression line. So again, let's go back to the superintendent's question. If a student meets our minimum attendance goal of 87%, what would their predicted test score be? How do we make predictions when we had a simple linear equation in Algebra 1? Well, let's find the y value when the x value was, say, 2. So at x value of 2, we're going to plug in, or we can look at the graph and look at x is 2. What's going to be our y value there? Well, we can plug in 2 for x and then solve for y. In this case, an x value 2 corresponded to a y value of 5 on our linear regression model. We can do the same thing here. If we want to find the predicted test score when their attendance is 87%, we're going to put in an x value of 87, and then we're going to find the corresponding y value by solving the equation when plugging in x is 87. That is 41.9 points. So we predict this student might score about 42 questions raw score right on this test about given their percent attendance. Now I want to talk about something really key here, the dangers of prediction. So let's get back to our central question. Will raising attendance also raise test scores? Look at this model. It's a strong, linear, positive relationship. Of course attendance helps. The more you attend school, and this is present in the data, the higher your test scores are. That's a really strong relationship. So in the past several years, superintendents have piloted large-scale and sometimes quite expensive initiatives to improve student attendance. These include programs where you're calling absent students and robocalling and in-person calling, hiring attendance case managers to work with students and coordinate getting you to school and coming and doing home visits, using Uber and Lyft even for students' transportation issues to make sure they get to school. They predicted if we can fix attendance, we can fix test scores. The result for most of these programs is attendance did improve. It improved a statistically significant amount. However, test scores, and this is for low-income students too, stayed flat. Test scores stayed flat. You might be wondering, what? How could that happen? If attendance proved we had a strong progress, how could that happen? So test scores overall did not rise, but the achievement gaps, because test scores stayed the same, remained. So let's get into a discussion about this. This is our model for thinking about why improving attendance would improve test scores. Why do you think raising attendance didn't work? Why could it not have worked? Given what we've seen in the data, why in these school districts did raising attendance not work? Have a good day, statisticians, and goodbye for now.